TU Wien in the research group Photogrammetry. And it's not only us alone, it's together with the geodesy and with the BFA, with the Bundesforschungszentrum für Wald. And as Lothar just said, in a lot of projects, redundant work is collecting data, harmonizing data, and we have seen that for ourselves in various different research projects, and we wanted to use the chance within TOPO4EO, or this is the initial idea behind TOPO4EO, to address this and change the way we are working and how we are accessing data. And this research project is actually targeted as vegetation. So we talk about countrywide geospatial data, raster data, but our focus within this project is on vegetation. And we talk about remote sensing in vegetation. We use a bunch of different sensors. So on the one hand, we have spaceborne sensors like satellites, so like Sentinel-1, Sentinel-2, if we refer to the ESA satellites, which have a medium to coarse spatial resolution, but they have a very high temporal resolution. And on the other hand, we are using, for example, LiDAR, light detection and ranging, mounted on various different platforms. This can be airborne, this can be UAVs, or it can even be ground-based. And these data sets provide us very accurate and very high spatial resolution data sets describing the geometry and the 3D structure of vegetation and basically of all objects and structures on Earth in very high resolution. And what we do in research, basically, if we really want to break it down, we want to turn these observations that are captured by those sensors into insights. So we turn these observations and turn them into variables, predictions, and other things that we can actually draw conclusions from. And a lot of questions we are addressing in this regards are related in various different keywords, are related to very prominent topics in the recent years. So on the one hand, of course, climate change and how vegetation reacts to climate change, but also in which way vegetation affects or counter-interacts climate change. Its forest, for example, plays a critical role in the green transition in two different ways, but also the Europe Green Deal, which is also underlined in green by now, but also the EU renaturation law. So in all these topics which popped up in the recent years and which are very important topics, remote sensing in the context of vegetation is an important topic. But if we want to come from observations to insights, we need something in between. And if we want to put modern research in a nutshell, then one could say that it basically revolves around models. So in the center of a lot of research, there are models. And this can be deterministic models, but more prominently, of course, these are machine learning models, probabilistic models, deep learning models. And what those models, or how we interact with them, how we use them, basically is, so we take a bunch of input data sets, which are describing our various different objects or structures we want to observe. So these can be digital terrain and surface model, for example, which are derived from LiDAR or from photogrammetry, so from image matching, if you talk about surface models. These can be autophotos, which were acquired by airplanes with cameras. Of course, these are satellite sensors, Sentinel-1, Sentinel-2, there are a lot of more. And of course, these can also be arbitrary other sensors or information like the Inca dataset, which is a meteorological dataset provided by Geosphere, which contains various different meteorological parameters, which are also very important drivers for various changes. So we take all of these parameters and observations, we put them in such a model. Those models are very powerful in extracting certain patterns and structures from the data. And based on those patterns, they derive some certain predictions or variables, and this really depends on the respective application one is dealing with. So this can be land cover, this can be forest mass or tree species, but this can also be land sets. So we see these input data sets, they are quite frequently used in a wide variety of scientific disciplines and in a wide variety of questions. And if we now look at this very simple way of looking at modern research, then we can break it down or divide it in three major individual steps. So the first one, as Lothar already said, it's the collection and often also the harmonization of data sets. So as I said, with all these different input data sets like sentinels, so satellite data, terrain models, surface models, orthophotos, they come at different spatial resolutions, they come at different temporal intervals, they come in different formats, everything you can name it. So in order to use them together to come from observations to insights, we need to harmonize them and homogenize them. The second step obviously is the development and training of methods. And the last one is, of course, that we need to evaluate what we have done and what our outputs are. So, and if we look at those three steps, and I think there are a few people here who see themselves, who work in this kind of workflow. Yeah? So I just wanted to ask, if you look at those three, which one of the three tasks would you say you prefer most or you're most excited about to work on? Just raise shortly your hands. So would you say it's the collection and harmonization of data? Okay, 1, 2, okay. What about the development of new methods and gaining new insights from the data? Okay, so it's a lot more, that's a good thing. And the last one is the evaluation. It's part of the game, so we need it. So a few people, so most people actually said the most interesting part is the development and training of new methods and models to gain new insights. And now I want to phrase the question differently. In which of the three topics, if you think about the research project, if you think about other projects, which of the three is the one where you spend most time on? Is it the collection and harmonization of data? Yeah, there are a few more hands than people are interested in, that's good. Is it the development and training? No? And the evaluation? Partly. So that's a good thing. So in the first question, the most people actually raise their hands. They are most interested in developing new approaches and gaining new insights. That's the exciting stuff. That's what method development, I believe that's really what people go for research. But we end up doing, not most of the time, but a large portion of what we actually do is spending time on the first step, the collection and harmonization of the data, that we can finally get to the second part. And this is actually what we, as research department and everyone else, probably experienced all over again, that with every project you always start with the same thing and you always or sometimes repeat the same steps. And we thought there must be a better way, and we need to reduce this amount of redundant work, that we concentrate on the fun stuff again and not evaluation. And that's why today I don't want to talk about method development and evaluation, but I want to talk about the first part, the collection and harmonization of data, how we access data, and how we can change that, especially when we talk about multimodal data and countrywide data sets. How can we change and improve the situation that we can finally focus on the stuff that we actually want to do? So when you go back to this very simplistic view of modern research, and have a look only on the left side of the input data set. And so we can roughly divide these input data sets. So the first one is obviously the satellite data. So these, when you talk about Sentinel-1, 2, these are from ESA. They capture the data. There is central infrastructure. There are companies who are providing the data. It's all cloud-based. It's all centralized. So they are a little bit on the side. But if you look at all the other data sets that I mentioned, like the surface model, terrain models, the orthophoto, but also the Inca data set, or anything else that you might work with, like the Graphenintegrationsplatform, or you name it, these are data sets which are produced by national mapping agencies, by provinces, by local authorities, by different national stakeholders, basically. And so they are quite different from the way the satellite data is produced, but they are also quite different in the way they are distributed and you can access those data sets. And now you could say, hey, stop a minute. All of those data sets that you mentioned, they're already OGD. So why are you going to talk 40 minutes about that? So that's not very interesting. And you're right, all of these data sets are already OGD. But if we have a look at the OGD landscape in Austria, we see that although they are OGD, there are still certain obstacles and barriers we need to overcome to really exploit the full potential of those data sets. So I just had a look at Geoportal Inspire GVAT, and there by now there are listed 1,310 data sets, which is really amazing. I mean, I started working in geodesy in this field, I don't know, 15 years ago, and probably there were, I don't know, 100. I have no idea. I hope that I could derive some statistics to see the increase over time, but it wasn't that easy. But the progress we have seen in OGD data in Austria, and especially also the quality and the resolution of the data sets that are available, if you compare this now with 10, 15 years ago, it's amazing, so don't get me wrong. And especially as it's not only 1 or 2 or 3 organizations, but it's 70 plus organizations. So it's really widely spread among various different stakeholders and areas. But on the other hand, those data sets are distributed over 10 plus geoportals. I didn't count them, but you have each portal of the provinces. You have the portal of the BAV, you have the portal of the geosphere, you have the portal of the BFV. So you have various different portals where you can access and download the data. And inherently with that, you have also 10 different ways on how you download data. So in one, you have a GeoViewer where you can click the individual tiles. So also the ways you can access and download the data is very, very different across those. And on top of that, we don't have one coordinate system and reference system in Austria, but we have a multitude. So I only looked at the document which is provided by the BAV, which is the EPSG Austria, where they list all the EPSG codes which are used by the BAV. And so we have 26 projections and 10 different reference systems, so planimetric and height reference system combined. And if you look at all of this together, I came up with a slight formula. So we have this 1,310 data sets. So they are distributed over 10 different portals, so we divide it. But in multiplied by 26 projections, we have a quite Kuddelmuddel. Yeah? And with Kuddelmuddel, I don't say that we have a Kuddelmuddel on the data, but this introduces a Kuddelmuddel when we want to work with the data as researchers, because we have to somehow correct this Kuddelmuddel and bring it on a straight line in order to really exploit all the insights and all the amazing things we can do with these data sets. So what's the situation like in TOPO4EO? So this was the big picture about the whole OGD landscape in Austria. So let's talk about the data that we are actually interested in when we talk about TOPO4EO, or what we are actually interested in when we talk about remote sensing in vegetation. So on the one hand, we are obviously interested in the DTM and the DSM, because they basically give us the geometrical properties. We might use the orthophoto, not only in the visible domain, but there is also in the near infrared. And of course, we might want to use Sentinel-1, Sentinel-2. And I already listed here the providers. So the first two are already provided by the BAV, by the Open Data Portal by the BAV, the last one by the EOC. So we only have 2 different providers, which is we are already off to a good start. So let's look at the resolution. And so the DTM and DSM is available in 1 by 1 meter, which is really amazing. I mean, until, I don't know, 10 years ago, the highest freely available terrain model for whole Austria was 10 by 10 meters. And now that we can just use the 1 by 1 meter, I wouldn't have dreamt about that 10 years ago. So this is really amazing. If you look at the orthophoto, the situation is even better, because here we are at 20 centimeters. I mean, 20 centimeter orthophoto just for free to use it however you want. This is really amazing. And last but not least, obviously, we have the satellite-based data, which is a 10 meter resolution, so we already know that. So we have quite a variety of the resolution of the input data. And now we come to the projection. So obviously the DTM and the DSM, they are provided in 3035, which is the LBI projection, which comes from the Inspire guideline, which tells you should use that, which is already good because it's one coordinate system for the whole data set. But if you look at the orthophoto, we already see, okay, there is slightly difference, because here we are in MGI in the 3 different strips. And obviously, if you want to use those data sets available, we have a little bit work to do. And lastly, we have the satellite data. And here the situation obviously is slightly different, because this is not Specifically for Austria, it's global, so obviously they are using a different coordinate system more suitable for their purposes. And lastly, and more importantly, and this is what's mainly today about, can we access the data via their metadata? And this is really, really crucial if you want to automate things, if you really want to process things in a very convenient way. And here, unfortunately, the first two, like the DTM and the orthophoto, those you can download those data sets and you can download the metadata. It's provided, but it's not provided with the data. It's really some metadata. It's auxiliary, so it's as a shapefile, as a geo package in a separate file. In contrast, if you look at satellite data, here the premise is completely different, because here the metadata is the entry point that you can access the data. And this is slightly the other way around in the way we normally or traditionally addressed or accessed such high resolution data. So if we want to overcome this and really want to start change and use those data sets together, we need to probably address a few things. So the first thing is we want to use the DTM and DSM together, and using the orthophoto in 3D strips is a little bit awkward, so we decided, okay, let's bring that also into the layer projection. That's a reasonable assumption, especially if we think about, not about Austria, but Europe. If we provide the outputs also in the layer projection, it's also conform to other countries, so that is a reasonable assumption and a very good point. The second thing is we really need to change the way we access this data. So downloading the data, that's fine, but if you So the BAW, it's not only one release, so they release multiple different releases. So if you look at all of them, it's over 10. So always downloading manually all tiles, doing this stuff over and over again, that's just annoying, and that's just redundant work. So we need to change the way we are accessing this data. And lastly, we have to address obviously the topics about the different spatial resolutions, but if you really want to combine the orthophoto and the DTM, we need to bring them to the same resolution. But obviously now saying, okay, because of our use case, we are going from the 20 centimeters to 1 meter, that's just our use case, and we would lose information, and other users want to have the highest resolution. So in that case, we are not saying that we change that permanently, but we want to provide auxiliary data and function and tools basically that allow users that have a slightly different use case to properly do that, because everyone knows if we do reprojections or if we do rewrapping, resampling, it depends which resampling method to use. In the reprojection, it depends, are you using the global 7-parameter Helmholtz transformation, or are you using the GIS grid? So these are potential error sources that we don't want to fix from the beginning because they might be different for different use cases, but we want to address it anyway. And now you might say, okay guys, that's you. It's nice that you're interested in deriving countrywide products and you want to combine those, but then do it, but leave us alone. But it's not only us. I would like to say that we are so advanced and so state-of-the-art that we are the only ones who are using deep learning models, which obviously is not true, and we are the only ones who are addressing this topic at a country scale. But it's all over Austria, people are using this. And it's not only academia, it's not only research. I mean, research is a big part, but it's also other companies, it's other stakeholders, it's other national agencies and national organizations which are also interested in deriving insights from observations at the Austrian, at the country scale. And what this means, that all of the steps that I described earlier on, in our opinion, causes really 3 major points that really affects the way we conduct research or how we work with these data sets. And the first one is, I'm pretty sure we are doing a lot of redundant work. I really don't want to imagine how often a normalized surface model was already derived from these input data sets, or how often a slope was calculated from these input data sets. And it might not be for whole of Austria, but even if you're only interested, for example, in Vorarlberg and Tyrol or in Salzburg, these will be overlapping bounding boxes or areas which just creates redundant work. So if we would provide certain things once in a good quality controlled, this would reduce a lot of avoidable redundant work. The second thing is we could reduce potential error sources. As I said, reprojection, resampling, all of these steps always have the potential to mess with your data. If you're using nearest neighbor for resampling and not b-cubic interpolation, for example, you introduce artifacts. Everyone who's done it with a terrain model and calculated a hillshade afterwards knows the nice artifacts. You see them in the hillshade. So by providing people with tools or with functions which they can rely on and which have been tested in this framework helps. And I mean, I studied here, so I have a certain background in geodesy and I should understand all of those things we are doing with coordinate systems and reprojections. But most of the time I'm also guessing and just controlling the results to see if they are where they should be. And there are a lot of people who come from, for example, from glaciology, geomorphology, where the geodesy part is not so essential. They don't have such a strong background. So for those people, probably reprojections, coordinate system, reference system transformation, these are even much more magical things. So I believe we really have here the potential to reduce error sources. And lastly, it's just wasted resources. Because in every research project, Lothar just mentioned that it's 15%, you always have one work package or a bunch of time dedicated to pre-processing. It's 4 months, 6 months, whatever. And a lot of this pre-processing, we could get rid of that. And this would really allow us to move this time to the actual funny part, which is the method development. So this is very, very closely related to the wider redundancy, but it's not only human resources, it's also computing resources. So if 10 institutes in Austria reproject the orthophoto at 20 centimeter resolution from MGI to LBI, for example, that's 10 times a bunch of calculations which we could use otherwise. And I never thought about the costs of such things, but since the whole discussion about what one ChatGPT query costs like, it's really coming to people's mind that computation is not for free, it's really costing resources. And I believe from that point of view, we really need to think about that as well. And this is at the core, and this is the idea of TOPO4EO. And as I said, it's not only us, the TU Wien, it's together with the geodesy and it's together with the BFW. And we applied for it, we submitted this proposal in the course for FFG call in the course of the Digital Twin Initiative in the first one. And we are lucky to have the potential to work on that. So what are the actual aims of TOPO4EO? So the first one, obviously, you should have guessed by now, so it's really about unified access to the data, but not only the data, about the metadata as well. So we really need to change the way we access those data sets and how we interact with those data sets. Because within this there is a really huge potential to improve the way we work with these data sets. The next step is that we provide auxiliary tools and data, as I said, to somehow control how people resample, reproject data, but also derive additional data sets that we think might be useful. So one example, if you have the DTM and the DSM, why not also provide the normalized surface model? Because I believe that's most of the times the first thing when you download both you're doing, so why not directly provide it as well? The last thing, as it's a research project, it's not enough to say, hey, we are setting up some infrastructure. Obviously, we also want to use this built-up infrastructure to do some method development and to improve certain products. And this is within the use cases where we selected 3. The first one is actually I will present on one slide later on, and 2 more which are on the one hand the improved estimation of above ground biomass, and the last one is the detection of natural retention ponds, where we also are exactly at the intersection between a terrain model at the core and also how to use Sentinel-1. And the last one is, if you build something like this, or if you plan to establish a new way of accessing data, you always need to think about, or you need to bring people on board. And obviously in that case, the outreach is really important, and that's why it's a very, very good opportunity, and we are very happy as a consortium to present our ideas and to talk about our ideas today within this venue. So let's look at more detail how we realize this unified access. And it basically boils down to two core elements. And for those people who are regularly working with satellite-based data, they are by now probably very common things. So the first one is, and we start with the left side, is that we use formats that are optimized for cloud access, because we want to move the data from storing it locally by individual users to a more centralized solution. And obviously for that we need formats which allow that we efficiently access them remotely. And as we talk about raster products, obviously the one format that is very well established is cloud optimized GeoTIFF, or short form COC in short term, which has the very neat and nice advantage that you don't need specific interface, you don't need a specific API or a client, you just can access the data via simple HTTP requests, which is very efficient, and you don't need specialized software or any interfaces to access them. So this is already a good step forward. But as I said earlier, it's not only about data access, but it's also about finding data. And here, STAC, Spatiotemporal Asset Catalog, in the last 5 years, Christian, I don't know, 5 years, really established itself as a very common way of representing metadata for satellite data. And STAC itself, its vision or its idea is that it's not about a product, it's not about satellite data, it's not about raster data, it's about spatial temporal assets. So this can be point clouds, this can be vector data sets. So it should be a common format which is in Panama the underlying format. And it's a very simple and very efficient way of representing the metadata, make it searchable, and through that make the underlying data accessible. And so I concentrate on this part here, because that's actually really the great benefit that we see. Because COC, also a cloud optimized GeoTIFF, is already quite often used, but on top of it we need also a way to access the data through this metadata that we can really exploit the great benefit. So what's the current situation about the metadata of those two datasets, like the terrain and surface model and the orthophoto? And as I said, both datasets come with metadata, but those information is provided in additional form, like in a geo package or a shapefile, a PDF, and you see the output here. So on the left-hand side, you see the acquisition times basically of the digital terrain and surface model. So when the data was acquired by airplane, basically. And what we directly see is that we have a huge variety of the acquisition data. So in some regions they are very current, 2023, 2024, but in some regions like in Styria and Corinthia, they are already 10 or 15 years old. And of course this is an ongoing process. So all the provinces continuously gather new data, they process it, and so this is an ongoing process. But this basically shows how important it is that we can access this information, because it's important for us to know if the data we are working with comes from this year or if it comes 15 years earlier, because this makes a huge difference, right? And on the right-hand side, you see it for the orthophoto, and for the orthophoto the situation is slightly different, because I think every region in Austria is recaptured every 3 years, I believe. Is it 3 years? 3 years. So we see we don't go back 10 to 15 years in time, but still we have also a variety of the acquisition times. And if we want to not only access the data, but also know when the data was acquired, and if we want to filter data by its acquisition date, because we want to say, hey, I only want to work in regions which were captured in 2021, because I have a certain question related to the time, then it's important that we can access the metadata and the data in a very convenient and uniform way. And how do we come from this basically to a queryable metadata? And this is the underlying idea behind STAC, which is just turning metadata in a simple JSON format. It represents, so the idea is that we create individual tiles, and for each tile we derive all the metadata. All these tiles together form a catalog, and this catalog can be searched for by its metadata. So it's very straightforward to turn this information into something that can be really searched for and can be looked upon. So how does this look like? And for the terrain, for the surface model, and for the normalized surface model, we already have done that. So there's the so-called stack browser, which is also provided by geodesy, which is a very visual way of looking at the data. And we created one catalog for each of those entities. And if we go into this catalog, it consists of all the tiles that we created. And for each tile, you now have all the metadata available. So it's some general description, but you further have also, and this is the important thing here, if you only talk about the temporal domain, you also now know for each tile when this data was acquired. And how do we come to that? If you remember the slides, 2 slides before, we basically use the bounding box of each tile as a cookie cutter and cut through the geo package and look within there what's the earliest acquisition date and what's the latest acquisition date. And by that we can already somehow obtain at least a rough approximate acquisition time. So it's not up to the date, but at least we can boil it down to the year. But this stack viewer is only one way to interact with the data. So when we have something like a metadata, so when we have something like that, we want it to be very general, that we can access it from various different clients. So this can be, on this example, QGIS, or the next example I will show is Python. So in the newest QGIS version, the stack loader or the possibility to load stack item is already integrated into the core of QGIS. Before that, it was an external plugin which had to be installed, but in the newest version, it moved to the core. This means that it's also about maintenance and about the long-term availability of this feature. And what this means is you can just connect to the geodesy stack catalog. You can select the collection you want. In our case, it's the digital terrain model collection. And then you already obtain a bunch of tiles which are selected. And the one tile you selected, the bounding box is already previewed in QGIS. And I don't know if you see it, but all the other tiles that are loaded are very transparent, already shown. So you know where each tile basically is located, and you can nicely interact with that. But we can also use QGIS to filter our data. So we can search by the spatial dimension, we can also search by the temporal domains if we want to narrow it down. And furthermore, we can look at all the information that we could also look at online, basically. And the very neat thing is we can also directly download the tiles from within QGIS. So we can not only look at the metadata, but we can really also access the underlying data. And that is the nice thing, that through accessing the metadata and looking through the metadata, we also have a way of directly interacting and downloading the data itself.
But you don't need to download it.
You don't need to download it, no. But if you really want to work locally with it, then you can download it, yes. But most of our workflows, especially when we talk about deep learning or machine learning, Python established itself as a very important programming language because it brings all the libraries and everything you need to conduct those kind of workflows. That's why also Python is very prominent within science, and somehow is a successor to MATLAB, I believe, because I think not people use MATLAB anymore. I don't know. So, and only with a bunch of line of codes, basically, you connect again to the collection, you specify an area of interest, you say you only want the newest release, or the latest Stichtag from BEF. You are able, with a bunch of line of codes, you are able to access all the footprints and all the data sets, basically. But we can also go a step forward, and that's the very neat thing about accessing it through Python. So you're not limited to individual tiles, but you can also query or directly access a larger extent, which expands beyond one tile. And on the server, all those tiles are merged together, and you end up with a continuous geotiff of the whole region that you have defined. So we are not limited to individual tiles, but we can really download and access exactly the data that we are interested in. So if you have a certain study area, if you have a certain training area, whatever, it's very easy and it's a very convenient way to access the data. So you don't need to download all the tiles that basically bring together your study area, but you can really access the data as you need it. So when we go a step further, so when you look at the auxiliary tools and the data we also want to provide, so now we somehow, with integrating all those data sets into Stack and converting them into a cloud-optimized format, we somehow unified the access and also unified the way we can interact with them, at least partially. So the next step is somehow in order to really use them combined, we further need to align the data sets to each other. So as I've already said, we have different resolutions. So in blue, it might be Sentinel-1 raster. So in green, there might be an orthophoto DTM. Don't count the cells, it's not 10 by 10 because I was too lazy to draw more rectangles, so I stopped at some point. But obviously, in such a way, we can't use those data sets together, because what we want is, we want to have them aligned, that we can really, for each point in Austria, basically, we want to have we want to be able to basically cast a ray through time and get all the observations that are available. Either it be Sentinel-1, Sentinel-2, or it's the terrain model, the surface model, the orthophoto, whatsoever. And in order to achieve this, we need to come from this to an aligned, basically, data cube, which allows us exactly this kind of process. And as I said earlier, this involves reprojection, resampling of the data, and this really depends on the individual use case in which direction you want to go and which data sets you are going to combine with each other. And in that respect, this is exactly one of the auxiliary tools or functions we want to provide. But as I already also said, it's not only about auxiliary tools, it's also about auxiliary data. And one of them I already mentioned is the normalized surface model, because that's something that's very commonly used and which is very easily derivable from those input data sets. But especially when we look at the digital rain model, there is slope, there is aspect, there is curvature, there are a bunch of different topographic parameters which might be interesting depending on the use case. And here we really want to derive a subset which we believe is used by a wide variety of users. And here we are also very open to recommendations from other people who are using that say, hey, this would be a real benefit not only from us but also for other people. It would be great if you could add this. And obviously, last but not least, it's also about your data. There are some people here who also act as data providers. And of course, such an infrastructure and such an idea lives from the data that it's contained. And as larger and as wider this data, this collection gets, the more users and the more potential we basically can generate from accessing, changing the way we access data. So one of the use cases I want to show a little bit more in more detail is related to forest anomalies or forest disturbances. So we start again with the acquisition times of the terrain and especially of the surface model. And as I said, there is some region in Austria where the data is 15 years old. And now the question is, if I have a surface model which is 15 years old, how representative is it still today? So can we really use this data anymore to derive anything, or doesn't it represent the current state anymore? And the basic assumption is, if there are no disturbances, man-made or by weather or whatever, and there's just a natural process, then vegetation does not change that much over 10 years. I'm looking at Markus. He's okay, it's not completely wrong. So there we can say, okay, the surface model, it's not perfect, but it's the best we have and it's still representative. But how can we identify those regions where those older data sets are still representative and not? And this is exactly where, again, Sentinel-1 comes into play, because since 2014, Sentinel captures every 5 days observations. And the neat thing about Sentinel-1 is obviously that it's not influenced by clouds and everything else, so we also get observation when it's very cloudy. And if we look at two timestamps of Sentinel-1, 1 year apart, and there happened something with the forest in between, it may be windstorm or snowbreak or whatever, or logging, then we see that in the signal. So we can use differences or the time series of Sentinel-1 to basically give us a further mask or an additional layer, an auxiliary data, which can tell us on how, oops, that was too much, on how much we can rely on the surface model, or if we say, please, better not use it there because we see that there's something happening in between. So what's the current status of our activities? So regarding the DTEM and the DSM, all releases, or alle Stichtage which were provided by the BEV are now available via the stack catalog, as I showed earlier on, and can be accessed through them. For the orthophoto, it's still ongoing, because going from 1 meter to 20 centimeters and processing it for the whole of Austria introduced more problems than we initially expected, so it takes a little bit longer than I assumed. Regarding the auxiliary products, as I said, the normalized surface model is already finished, and the derivation of other products is still ongoing, and we will continue that. The auxiliary functions is something also we continuously add and integrate, because that's also something that we need for our work. And lastly, the demonstration materials, this is something that I come in the next slide to it. This is also something that we continuously update and process. And this brings me to the last topic, to the outreach. And so now I already talked 42 minutes. So of course I could now brief examples and workshop something for the next 20 minutes, but then probably everyone would have fallen asleep by that. So that's why I decided it might be a better idea to split the hands-on experience to a different slot. So next week on Thursday from 2 to 3, we want to provide all interested users with a hands-on experience on how to use the infrastructure that we have building, and how to access those data sets, the DTM, DSM, and normalized surface model, through the stack catalog that we created. And that's not something that I'm going to do, that's going to my colleague, David Simberg, who also prepared all the examples. But everyone who is interested and thinks, well, that might be a good idea to use it within my boundaries, but for my research, it's very welcomed, and please forward it also to anyone you think might be interested. And if I haven't persuaded you that Stack and all the initiatives that we've done so far is a good idea, then next week is a good idea to finally get convinced that it really changes the way we can interact with data. So what I want you to take home from today's presentation. So the first thing is embrace time series. And what I mean by that is that like the BEV is doing, so they release multiple versions like 21, 23, 24, so the Stichtage, which provided with the possibility to really create time series also of the surface and the terrain model. Although not all regions have changed within this time, some regions have done, and this allows us to really see what has changed. So don't think about only the current release and only a current version of the data set, but really provide all the versions or the continuous progress, because this really provides us with additional information that is really useful for various topics. So why I concentrated on raster products today, it's not only about pixels. So obviously we have seen from this 1,310 data sets we have seen in on Geoportal Inspire, only a small margin are raster products. So we have vector products, we have point clouds, everything. And obviously within such a research project we can't address everything and solve everything. So that's why we concentrated on those products that we actually benefit most from ourselves. But it's not only about pixels. So the same idea works as well for vector geometries, it works for point clouds, it works for everything else. So that's why I really want to mention that the same idea can be applied to anything else as well. lastly, this is more addressed to data providers. When you talk to people, you sometimes hear, yeah, people don't ask for the data, so they don't have any use case for that, or no, we don't see that people are downloading it. But the point is, don't wait for users. Create them. Because in the end, people start using the data if they are able to access them and if they are able to work with them. And if we tear down the last barriers that we currently have in accessing the data and really make it more easier, I'm persuaded that more people are going to use and start working with these data sets. And I believe that if more people are using these data sets, more innovative ways of working with the data and more innovative products will result from that. So it's really important. And last but not least, again, addressed to the data providers, a lot of the research we are doing currently, not only TU Wien but general, is based on open government data. It's based on surface model, orthophotos, whatever else. So by that, you are basically drivers of innovation, to put it plainly, because without those data sets, we couldn't do what we are doing, and by that, we couldn't exploit the full potential of those data sets. And this really shows that how important it is to provide data through OGD and not stop right at, okay, we provide a download link, but let's go the next step in really making access to those data sets much more easier, that we can fully exploit these resources. Thank you for your attention.